Okay, so let's have some fun with layer 3 VPNs. Okay, so we're going to really just get into how they work to begin with, and then after that we'll get into how to configure them. We're going to really define the roles of the various routers that are going to be involved in this process. We've got our P routers, our PE routers, and our CE routers. Of course, the P's being the provider cores, PE, provider edge, and CE customer edge. We're going to get into an addressing format, which is the VPN IPv4 addresses. So we'll look at how they are set up. We're going to discover this thing called a route distinguisher and find out what it does. We are going to look at the flow of control information. By that, what we mean is routing information. How is the routing information propagated around between our routers? And then we'll take a look at how is the data forwarded across the network using our level shift paths. So, layer 3 VPN terminology, let's get into that to begin with. So here we have our various routers that are involved really in our provider core network and our customer network. We've got the CE routers, the customer edge routers. So they are the routers that connect the customer to the provider. So that is the connection to the internet service provider, the customer's connection. Then we've got the PE routers, which is the other end of that link on the provider network. And then we've got these P routers in the middle, which are just there to do routing across the provider's core network. So here we have these CEs. Really, they can use whatever access technology they want. You could have, for example, you could have a BGP peer between the CE and the PE to provide that connectivity, or you could have no BGP, or you could simply have static route. So the customer will simply have a default route pointing to the provider's gateway, and the provider could simply have static routes pointing back into the customer's network. That would work fine. You can have it as simple as that. Or you can have any other protocol, OSPF, or whatever, between the CE and the PE. So a lot of flexibility as to how that works. Then there's the provider edge router. The provider edge router is really the only routers in the whole of the provider's network that has to be aware of the VPN. The provider edge router. It maintains the VPN specific forwarding tables. It exchanges the VPN routing information with other PE routers using BGP, and it will use MPLS level switch paths to forward the VPN traffic between PE routers. So the traffic will transit the provider's network via a level switch paths, which we're going to be configuring. Okay, so one of the beauties of this system, or one of the, I guess, the thing that makes it administratively efficient, and which means it's scalable, we can add lots and lots of customers, is that the only routers in the provider's network that aren't involved in this whole VPN process are the PE routers. No other routers are actually aware of the VPN at all. And the other really good thing about it is that a PE router only has to maintain VPN information for the customers that are attached to that router. So, and for the customer sites that are attached to that particular router. So it makes it very easy to add extra sites or extra customers for that matter. Okay, the PE routers, they forward VPN data transparently over established LSPs, and we don't know anything about the VPN. Okay, so what is a VPN site? Well, it's a collection of machines that can communicate without traversing the customer's provider backbone. In other words, a customer site is its own little administrative domain where the customer looks after their connectivity within that particular site. So does not require the service provider's domain. I mean, a site, a single customer site for this purposes could actually be, a customer could actually have, for example, an IPsec VPN from, say, one of their sites out to some other smaller sites, and because you've actually got none of that traffic traversing the service provider's VPN, as far as the service provider is concerned, that would all be just one site, even though there might be some IPsec VPNs involved in a single customer site. That's possible. So really, it's just a routing domain that the customer looks after themselves within that one site, and they provide all the connectivity within that one site. It could be as simple as simply one gateway with a switching fabric inside the site that connects everything inside the site together. That's the only router in the whole site is simply their gateway. So it could be as simple as that. So each VPN site is mapped to a PE router interface. That's an important point. So on the PE router, there is a dedicated interface for every customer site. So if I've got over here on the left-hand side, we've got a PE router with 2 customer sites. So they have a dedicated interface for each of those customer sites. Now, as you know, it doesn't have to be a physical interface, it can be a logical interface. Right, so I can have any number of logical units on a physical interface, and I can dedicate a separate one to each and every customer. So it's extremely expandable, extremely scalable, this whole concept. Okay, so we have these special tables which are called VPN routing and forwarding tables, or VRFs, as we call them. And these routing and forwarding tables are they're a routing instance of what they are, but they're a special purpose routing instance, and their job is to maintain the customer site routes. So what we've got here, if you look at how these routing and forwarding tables operate, let's just say we've got VPN A site 1. So here's customer red, there's our red customer there, VPN A site 1. So what we've got over here on PE1 is a VRF, a VPN routing and forwarding table dedicated to that customer site 1. So they have a table. What does that table contain? It contains all the network information that resides within site 1. So just say that customer within site 1 may have a couple of different networks. Let's just say they have separated their site into, let's just say, 3 different VLANs, for example. So there are 3 different subnets inside their site. Well, that routing table will contain information about those 3 different subnets that that customer is running. But that's not the only thing, because that customer has got 2 other sites as well. They've got over here site 2, and over here they've got the site 3, all part of that same VPN. So let's just say site 2 has got a couple of VPNs. Let's just say site 3 has got another 3 VPNs. Well, over here on PE1, that VRF is going to have information not only about site 1, but it's going to have the routing information, the network information about what's in site 2 and what's in site 3 as well. The reason it needs that is because when traffic is leaving site 1, destined for either site 2 or site 3, that traffic is going to hit that routing table and it's going to do a lookup. The router will do a lookup, and it's going to need to find those networks. It's going to need to find information in that routing table about the networks in site 2 and about the networks in site 3. Okay, so what's going to happen is that VRF is going to get routing information from site 1, which is relatively straightforward because it does have a direct connection via its dedicated interface to site 1. But here's the other thing that's got to happen. We've got to get routing information out of site 3 and out of site 2 across into that VRF. And guess what? They are private network routes. and they're not public internet routes, they're private network routes. So we've got to get private network routes out of these other two sites and get them into that routing table over there on P1. And that's not all. The VRFs over here on PE2 and PE3 that attach to site 2 and 3 have got to have the same information about the other two sites as well. So over here we're looking at PE2, it's got to have information about site 2, but also site 3 and also site 1, and the same goes for PE3. Its VRF, a customer red, has got to have information about not only site 3 but site 2 and site 1 as well. Okay, so you've got to have consistent routing information across all the VRFs so that traffic leaving, say, site 3, destined for, say, site 2, can do a lookup and its VRF and know exactly how to get to site 2. What is that lookup going to tell it? That lookup is going to tell it that it needs to go via a particular label switch path to get to site 3. Remember, we're actually using label switch paths across our network to forward the traffic. Okay, so there's two things going on here. There's getting the routing information into the routing tables. All right, that's our signaling, that's our control plane, that's our routing sort of plane. And once we've got that in there, then there is the forwarding of the traffic across the label switch paths. Okay, to get from one PE across to the other PE. Because really what we're doing is the traffic is going to, say we're coming out of site 3 heading to site 1, it's going to come out of the customer's CE, hit PE3, do a lookup in PE3's virtual routing forwarding table, and that's going to say, okay, your path to site 1 is via this LSP. It's going to put the traffic into the LSP, send it across to PE1. Across the LSP, it's going to come out of the LSP, then it's going to be directed to the Pacific interface that's connected down onto site 1. Okay, so the lookup, the routing lookup that it's going to do is going to say your next hop is an LSP, and it'll send it across the port to an LSP. So our challenge here, here's our challenge. We've got to get private routes to traverse across the customer's network into the various routing tables, so that they're all populated with private routes. But hang on, you can't send private routes across the internet. No, you can't. So there is a bit of trickery, a bit of magic involved in making all this happen. We need to get into that. Alright, so VRF tables. Is table populated with routes received from directly connected CE sites associated with the VRF table, and routes received from other PE routers with acceptable MP-BGP attributes. What does that mean? What's an acceptable MP-BGP attribute? Well, what that means is we're going to set up some import policies. That's what it means. We're going to set up import policies that say if the import policy matches this particular attribute, then we'll import those routes in. So what are we going to do? We're going to give the customer sites, we're going to associate customer sites with import policies so that we import the right routes from the right customer into that table. Okay, packets from a given site are only matched against the corresponding, the site's corresponding VRF table. Okay, so there is a dedicated VRF virtual routing, a VPN routing reporting table for each site, in each PE. Alright, now let's talk about how we get this done. Well, let's just say, for example, we have a situation where we've got customer red and customer blue there, with VPN A and VPN B, and let's just say, for example, these two customers are using exactly the same address space. So they're using the 10.1/16 addressing scheme, just by pure coincidence, as it happens, in their particular networks. Alright, well, we've got a problem. in that we potentially have got exactly the same routes being sent across our network, okay, across our provider network. So the problem is when PE2 gets those two routes, which are BGP routes, what it will typically do, the normal process is, it says, well, hang on, I have got two different paths to the same network. That's what it will see. It will see I've got two different paths to the same network. So what I'll do is I'll choose one of them. And that's what it would normally do. But we don't want it to choose one of them. We want it to accept both of them, because they actually are not two different routes to the same network at all. They're two different routes to two different networks. One is in customer site VPN A site 1, one is VPN B site 1. So they're actually to two completely different networks. Right? So what we have to do is we have to have some mechanism of making these two routes different. And that mechanism is called a route distinguisher. This bit here in green, this green bit is a route distinguisher. So this red bit, here's our route. Here's our original route that we started out with. This green bit is the bit we add as a route distinguisher. But while we're adding stuff, we also go ahead and add some other stuff that's going to tell us about, or is going to control, or set up, I should say, you're going to set up a label switch path for us that we need to send the traffic through. So this is going to provide some information that we're going to add into our label switch path that is going to control the actual forwarding of traffic once the traffic gets into the label switch path. Okay, so we add this thing called a route distinguisher, and the route distinguisher is a unique number that is different for every or for each virtual routing and forwarding table that you're operating on that particular provider's core. So every virtual routing and forwarding table has got a unique number for its route distinguisher. So you'll never have two routes which are identical, because we add this route distinguisher into the routing information. So what happens is this new route is what's called a BGP4 subsequent address family identifier, or the actual protocol is ACIT 128. Okay, so we end up with this new route, which is being created by the PE router. So the PE router creates this new route, takes the original route that it receives from the customer, from its directly connected CE, takes the route that it receives from the directly connected CE, adds this route distinguisher and an MPLS label and a mask, and creates this brand new route format, which is the VPN IPv4 route. NLRI stands for Network Layer Reachability Information, just in case you're wondering what NLRI stands for, Network Layer Reachability Information. So it adds this information onto the route. The format of it is this ACIT 128. Just don't be bogged down with jargon, okay? Just kind of get in your mind what's going on here. We get this route from the CE, we add this route distinguisher to it, we add some other information to it as well, which makes this route different from every other route. So we're never going to have two identical routes. So this is so it is all of this that is actually advertised to the other PE, and not just this red bit. Yeah, it's this whole thing that gets advertised over to the other PE. So the route distinguisher disambiguates the IP4 address, allows service provider to administer its own numbering space. So we're not sort of locked into or constrained by whatever numbering format the customer comes up with. We don't care what numbering scheme, what addressing scheme the customer comes up with, because we're going to put all this extra information on it and make sure that all of the addresses are different. Okay. So these particular types of routes are distributed by MP-BGP and uses this multi-protocol extension for BG4P. It's RFC there, which you can have a bit of exciting reading and read up on that RFC, and you'll get all about how that works. But the main point we're trying to make here is that this extra information is added to the route, so that the routes are all different. Also, we're going to use this information as well. We're going to use the MPLS label, for example, as part of the forwarding process. Alright, so a /32 IPv4 prefix will produce a VPN IPv4 prefix with a mask of /120 or 15 octets. So it's a rather long route that we are advertising here. Okay, and that's what we're going to see in our Juniper operating system, is exactly that. Okay, so what is the format of this route distinguisher? Well, we've got a couple of ways that we can go about setting this up. We've got type 0s and type 1s, these are defined by the RFC. If you're using a type 0, then the admin field, so we've got a type, so the type will either have a 0 or a 1 in it. The admin field, if you're using a type 0, the admin field is going to be the IANA assigned autonomous system number. So it will be the provider's autonomous system number will go in there. And then the AN field is a number made up by the service provider. So what you typically do there is you would have a separate number for every virtual routing and forwarding table that you're operating. They all have a unique number. And if we're using a type 1, so we get choose, do we use a type 0, do we use a type 1? It's totally up to the service provider as to how this is done, how you want to do this. In our labs, we're going to use a type 1 when we get to our lab. So in type 1, we have this admin field is 4 bytes, and the other field is 2 bytes. So typically what we do there is put an IP address into the admin field, and typically it is the loopback address of the originating PE is the IP address we actually put in there. And then we have an assigned number assigned by the service provider, which again makes really what you do there, you have a different number for every virtual routing and forwarding table that you're operating, so that every one of those is unique. So that makes it very easy then to sort of track down routes. Looking at routes, you can see, I'm going to track down some example about that. So this second example is kind of the way we're going here. So the 1.1.1.1, that is the router ID of the originating router. The 33 is the number which uniquely identifies that particular virtual routing forwarding table. And then we've got the actual customer's original route there, the 10.1.0.0/16. Okay, so that's kind of an example of what it would look like with a route distinguisher added. Alright, so as I said, the route distinguisher disambiguates the addresses. The ingress P router is the router that adds this route distinguisher onto the address of the routes it receives from its directly attached CE. Okay, so from its directly attached CE. The VPN IPv4 routes are exchanged between PE routers using MP-BGP. So the actual routes that are being exchanged across BGP are these big long routes with the route signatures attached. That's what's actually getting advertised out. And what happens is the egress P router converts this format into a standard IPv4 route and then puts those routes into the appropriate VRF, which is associated with that customer's VPN. So what we're doing, so the issue, remember I said right at the beginning, the issue is we've got to get these private routes and we've got to send them across the network into the virtual routing and forwarding tables that are attached to every site. So they've all got to be, all those sites have got to exchange routes. This is the mechanism that we're using. We're using this route distinguisher, and we're doing it using this MPBGP protocol to do that. Okay, so these routes with the route distinguishers are used in the control plane. So these are used to advertise and distribute this routing information between the PE routers. At the data plane, we are using MPLS, encapsulated IPv4 packets. Okay, so the actual packets are private addresses, and we are forwarding them across the wireless network, but we're not looking at the addresses, we're looking at the labels to achieve forwarding. Okay, so as we've said throughout this demonstration, this ambiguates the addresses, and here it looks like now with the route distinguishers added onto the routes. And the overlapping addresses are different because of the route distinguisher is different. Okay, so we've achieved that goal. So the two goals, the goal we needed to achieve is we needed to get the routing information from the other customer sites into our local VRF, and we needed to deal with the situation of or potential situation of overlapping address spaces of different customers. Okay, so we dealt with both of those issues by using the route distinguisher. Alright, so let's take a look at policy-based routing information exchange. So here we have our signaling plane, so routing information exchange between CE and PE routers. So that is fairly straightforward. That is straightforward because we've got an interface, a dedicated interface on the PE router that connects to the CE router. Okay, so that is exchanged across that particular link. The routing information between the PE routers is exchanged as we've just described, using the route distinguisher and using our multi-protocol BGP. The LSP are established between the PE routers using RSVP or LDP. In our labs, we're going to use RSVP for that. And the data flow is then forward, the traffic is forwarded across the label switch paths. Okay, so VPNs identified by administrative policy. What does that mean? That means that we set up the VPNs, the provider sets up the VPNs based on routing policies. So we're going to look at those, do a lab on setting all that up. The actual requirements of the VPN are defined by customers. What does that mean? The customer comes along and says, I have got 3 sites, and I would like a connection between the 3 of them. I need a certain amount of bandwidth, I need a certain amount of uptime guarantee for my particular connectivity. That's what I'm looking for. And the service provider then has to deliver that. Deliver the bandwidth, deliver the uptime, put in place stuff like all the protection mechanisms that are available to protect the VPNs, fast rerouting, protection, etc. All that will become part of the solution that the service provider will implement. Okay, so the logical VPN topology results from the application of export and import route targets. So what we're talking about is we have got lots of, go back to the previous slide. We may have lots of different routes. So let's just say we've got customer red and customer blue advertising these routes between the PE routers. How does the PE router know to put customer red's routes into customer red's VRF and customer blue's routes into customer blue's VRF? We don't want to get them mixed up, do we? No, that would be bad. Okay, we don't want to get them mixed up. So basically, we have a mechanism on within our BGP policy to filter. That's a new thing, route targets. Okay, so distribution of routes is controlled by BGP extended community attributes and VRF policies. We have this thing called a route target. That is our primary mechanism, making sure that we can identify which routes belong to which customer and make sure they are imported into only that customer's virtual or VPN routing and forwarding table, VRFs. We can also add, if we want to, if we need to, if we decide to, a site of origin route of origin information. So the route target is always used, and the site of origin may be used if the circumstances require it. So, what is this route target? Well, it has actually the same structure as a route distinguisher. This serves an entirely different purpose. The route target is part of an import function, an export and import function, whereas the route distinguisher is to make routes look different. So, pretty much exactly the same setup, exactly the same format. So, this route target extended community is used to export routes that belong to a particular customer, and then to filter on those routes when they are imported. So the attribute is added to the route on the export, and the attribute is filtered by the receiving router on the import. So a route target identifies a particular customer. That's ultimately what it does. Identifies a particular customer and their particular VPN. So upon receipt of a VPN IP4 route, a PE router decides whether to add that route to a VRF table. Import policies or explicit configuration. So there's two ways of doing it. We can have an import policy, or we can go and explicitly configure a route target as part of our BGP setup. So this will define which routes to add to a given VRF table. So route isolation between the VRF tables is accomplished through careful policy administration. Notice the word careful is there because you don't want to muck this up and end up importing the wrong customer's routing information into the wrong table, because that will result in data getting forwarded to the wrong place. Okay? Because your routing controls your forwarding, doesn't it? Your routing controls your forwarding. Okay. So, there are some tools available that service providers can use to structure this policy administration. So, they make sure that we don't mix up the targets, and make sure that we've got the targets applied to the right VRFs. Okay. So, let's take a look at how this works. Let's go through the whole process from start to finish. The CE device advertises the route to the PE router. Remember, there's a directly connected interface between the PE and the CE. So the CE advertises the route to a PE. Doesn't matter how it advertises, could be static, could be RSPF, RIP, let's hope not, BGP, whatever. Okay, so it could be any of those things. So the route arrives. The main point is the route arrives at the PE. Okay, so the PE becomes aware of this route, and therefore that route, because the interface that is attached to the CE is part of the VRF routing instance, that becomes a route or a directly connected route in that particular VRF routing instance, because that interface belongs to that VRF. So that is a local or directly connected route in the VRF. It could be a static route. It could be so you'll have a directly connected route, but you will also have other routes. And so you have other routes that may be static routes, maybe BGP routes, maybe RSPF routes. In any case, they will all arrive in the VRF because the interface that connects to the CE is part of the VRF instance. So all arrive in the VRF. That's step one. You might notice that we've got this MP-BGP session set up between our PE routers. That's already set up. So what happens next? The IPv4 address is added into the appropriate VRF. So there it goes. The routes arrive in the VRF. All happy. Now our mission is to get the routes from that VRF that is attached to that site across to the other VRF that is attached to the other customer sites. That's our next job. So the VRF table is configured to advertise the routes in the VRF table as layer 3 VPN routes using MP-BGP. So that's where all this route distinguisher stuff goes on. So all that gets added and then it gets advertised. We'll put all of that, all of those route distinguishers and everything out on at this point. So VRF table configuration also adds a route target community to the route. So there's a few things that get added on here. A route distinguisher gets added to the route itself, but a route target gets added into the route as well. So the VPN NLRI is advertised to other PE routers. So that's the Rico creating a route target, and could add, if you want to, a site of origin. So BGP next hop is the router ID of the advertising PE router. Alright. Next step. Each PE router is configured with an import route target. So the import route target is used to incorporate the VPN IPv4 routes into the VRF table selectively. So what happens is the routes are sent across the provider's network. They arrive first of all into this BGP L3 VPN table. That is a table specifically exists to receive these VPN routes with the route distinguishers and all the other stuff added in the great big SAFI 128 formats. Okay, those routes. So they will arrive into this BGP L3 VPN table, and then once they get into there, they are then imported into the specific VRFs table. So what gets imported into the VRFs table is just the private address route. So all the route distinguisher and all that stuff gets dropped off at that point. So it arrives in the BGP L3 VPN table with all the route distinguisher, the whole lot, whole kit and caboodle, it's all there. And then from there, it will then, the individual private address routes for the customer sites will be imported into their respective VRFs based on route target information, and what will arrive in those tables is just the private routes for the customer sites, and all the other stuff is left behind on the import. So each VPN IPv4 route in a VRF table is associated with an inner VRF label. So this is where the MPLS stuff comes in now. Okay, so we have an inner label to reach the advertised NLRI carried in the BGP update. And remember when we first looked at that great big long field with the green route distinguisher? There was this MPLS label sitting there. Okay, that's the label. That is the label value. So what happens is there is a label value that is generated by the PE router, sent across to the other PE router, and what that label does is that label is a unique identification of the specific VRF table that route belongs to. Okay, so let's just say CE1 has advertised some routes over to PE1. Now PE1 is going to add the route distinguisher, etc., 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 and advertise those routes across to PE2. As part of that advertisement, it includes the label value. Okay. Now what happens is when the label switch path is set up, that label value is added onto the label switch path. Okay, that is a label. But here's the thing, there are actually two labels that are added. Alright, the label that is sent across with the route becomes an inner label. And then when RSVP signals up the label switch path, it adds another label which is called the outer label. So the outer label is pushed at the ingress router, swapped across the P routers, popped at the penultimate router, we'll get into this shortly, and voila, the packet arrives at the end with that original label value that was put on by the originating VRF. Just follow this through and see how it works. So all routes associated with the same VRF interface can share a common label. Okay, so each IPv4 route installed in a VRF table can be advertised to the CE device associated with that VRF table. So what happens is the routes arrive over here in the other PRF at the other end. So they originated over in CE1, they get sent across from PE1 to PE2, and then they are re-advertised across to CE2. So CE2 site now has connectivity across to site 1. Okay, so over here VPN B on CE2 now has routing information that relates over to site 1, VPN B site 1. And that was sent across by BGP. And the connectivity between the VRF table of PE2 and CE can be static, it can be whatever, it can be BGP, ISPF, anything you like. Doesn't really matter. Okay, so that was the kind of like the flow of control information. Okay, well, let's take a look now at the control of how data flows through. So what we've got here is we have got a label switch path. So before we even start any of this, we've got a label switch path set up between the figures. So that is generally signaled up by LDP or RSVP. In our labs, we're going to use RSVP. Alright, so the CE device performs a traditional IPv4 lookup and sends packets to the PE router. So here we are, CE and PE, the data comes out of site, say looking at, in this case, VPN A site 1. Traffic comes out of site 1 over to the PE1, and it arrives on the interface which is associated with the VRF that is dedicated to that particular site. So what happens is packets arrive at the PE router. PE router consults the appropriate VRF table for the inbound interface. The two labels are derived from the VRF route lookup and are pushed onto the packet. So we have two labels, an inner label and an outer label. They're pushed onto the packet. Packets are forwarded using this two-level label stack. The outer MDLS label, that is kind of one that's this RSVP manages that one. That identifies the LSP to the egress PE router. So what happens next is the next hop is resolved using the INET.3 table, which is the standard way of resolving BGP next hops. So the result of that lookup is that the next hop becomes the label switch path. So the traffic is then forwarded into the label switch path based on that lookup in INET.3. Okay, we have this other label though. We have this inner label. The inner label identifies the outgoing interface from the egress PE to the CE. So remember when we first started off advertising that SASFI 128 format with the route distinguisher, etc., etc., we had an MPLS label. That label value was created by the originating VRF table sent across to the receiving PE, who then uses that label value as the inner label on the label switch path that's sending traffic back to that originating PE. Okay, so that inner label identifies the originating VRF table on that PE, and then specifically it identifies the interface attached to the CE on that label. So that's just, it's a label value. Okay, so what happens is identifies that egress interface communicated in the NP-BGP updates in the control plane that we saw earlier. After the packets exit the ingress router, the outer label is used to traverse the service provider. So we have the push, and we have the swaps all the way along. It will arrive, and at the point here is the P routers are not aware that there's a VPN, they don't need to know about it at all. So the P routers are just swapping the outer label. The inner label stays there unchanged the whole time. So the outer labels are swapped all the way along the label switch path. It then arrives at the penultimate router where the outer label is popped. So the outer label is popped and the packet is forwarded to the egress router with its inner label. The packet arrives at the egress router. The inner label identifies to the egress router which VRF table is associated with that LSP. So that packet is then sent to a specific VRF table and to the interface in that table that is attached to the CE. So it really identifies the outbound interface. So it is a forwarding information where that label value, the next hop for that label value is in fact an interface. So within the MPLS table, the next hop for that label value is the interface in the VRF table that connects to the CE. And that is the next hop. So the packet is forwarded to the label is removed, label is popped, and the native packet is forwarded to that interface down to the CE. Okay, simple. All right, so what we looked at the roles of the P, the PE, and the CE router. Describe the format of VPN IPv4 addresses, explain the role of the route distinguisher, look at the flow of this control information, which is defined in RFC 4364, and look at the flow of the forwarding information, the actual data flow. Okay, so we've got control information going one direction and the data coming back the other way. Right, very good. All right. Can you describe to me the roles of the PE, and CE routers? What does the P router do? What's its role in the scheme of things?
Forward shipping data.
Exactly. It is there to forward the MPLS data. It just forms part of, it's a transit router, or it may be an ultimate router in the label switch path. Okay, it knows nothing about the VPN. What about a PE router? What's its job? What does it do? Rather a lot, actually. Rather a lot. What does it do? What do PE routers do?
Exchange VPN routing information with the other PE routers.
They do. So they set up an NP-BGP peering arrangement with the other PE routers. They exchange the specific VPN route. So this is with the route distinguisher added and the label added. So all that's added, they exchange those routes with other PE routers. They also maintain the VRF tables. Okay, for each individual site that is attached to that particular PE. Okay, so they maintain those tables, and they also manage the export and import of routes to and from those tables. Okay. And the CE routers, what do? They are located where? In the customer site, so they are actually the customer routers. Okay. Now, in a layer 3 VPN, those customer routers are managed by the ISP, so they actually manage by the service provider. They're not actually managed by the customer or they're actually managed by the internet service provider who manages the customer's routers for them. Okay, that's part of the outsourcing. So you actually go on site to the customer's site, you set up the routers on their site, get it all set up for them, and manage this whole process. Right. What is the format of a VPN IPv4 address? Oh, there's a few bits to it, isn't there? A few bits to it. There is the original customer route. There's another bit that we add to it called a route distinguisher. Okay, route distinguisher. We add that to it. Alright, we also add an MPS label value into it, and there's a mask in there as well. What does the route distinguisher do? What's its job? What problem does it solve? What is the main problem that it solves?
Administering numbering space.
Exactly. So what it does is it deals with the problem of different customers using exactly the same addressing, IP addressing schemes, or using overlapping IP addressing space, which they could, of course, do because that's their own network, right? It could happen. It deals with that situation by making every route different by adding this extra information to it, the route distinguisher. Okay, describe the flow of the control information. Well, there's a bit going on there. So, the PE adds the route distinguisher, the MPLS label, advertises the route to the other PE. What else does it add? It also adds a thing called a route target, and it could also add a site of origin. Okay, now they are added as a BGP attribute. It's called an extended community. So one of the attributes of a BGP route is a thing called community, and a route target is a type of community. Okay, so it's called an extended community because it's been added specifically for VPNs. So it sends all of that across to the other PEs. The PEs import that into their there is a layer 3 VPN routing table. So they import that into that routing table. They then, those routes are evaluated by import policies on the respective VRFs to see if those routes, if the route targets match the route targets that are configured on the VRFs. If they are, those routes are imported in to those VRFs. And then they are advertised to the attached CEs. Across that link. So that is the kind of the control information, and then there's the forwarding information where there is a route lookup done based on the INET.3 table. So if you do a route lookup, you find a label paths. You also find information in there about an inner label and an outer label. They will push two labels onto the packet. The packet will traverse the LSP using the outer label, which is swapped all the way along, pop at an alternate router. It will arrive at the egress router, egress PE, with its inner label. The next hop for the inner label will be an interface, and it will be the interface that is attached to a specific CE, okay, which will be associated with a specific VRF. So it will be, the next hop will be that interface. It will be sent to the interface to the CE. Okay. Alright. And that's the forwarding line. Alrighty. What we're going to do, we're going to set up, we'll do lab 6. So we've got a bit of time before lunch. What we'll do before lunch, we will look at the configuration of how to set all this up. And then after lunch, we're going to build our baseline. And then we will build our VPN. Okay, we'll build our VPN. That's after lunch. So before we go to lunch, we're going to look at the configuration of all of this. Let's have a look at that. Down here, configuration. Okay. So basic layer 3 configuration. Here we go. We're going to look at how to set all this up. We're going to set up a routing instance, assign interfaces, create routes, import routes, export routes. For the routing instance, we're going to use route distinguishers and route targets. We're going to look at the purpose of BGP extended communities, configure and use those communities, list the steps necessary for proper operation of the PECE dynamic routing protocol, and configure a simple layer 3 virtual private network using a dynamic PE and CE routing protocol. What do we need to do first? First of all, we need to configure IGP. We must have a working IGP on our provider core, which will encompass all of our PE and P routers. Then we need to set up the MP BGP peering amongst our PE routers. We need to enable a label switch path signaling protocols, and we need to establish an LSP between our PE routers. So that's what we need to do first of all. Routing tables. INET.3, of course, is our main routing table for our IGP and BGP. INET.3 is going to be used, will be populated by the RSVP and LDP routes for our LSPs, and only BGP can look in that table. And of course, MPLS0 is our table which tells us the label incoming label values, outgoing label values, and next hops. Okay, we have this VPN name on INET.0 table. This is actually where the unicast IPv4 route. So this is our VRF table here. So these are the tables that belong to the customer's tables, and there's this BGP L3 VPN table where the unicast routes are received. So that's the great big long ones with the route distinguishers and the MPLS label. Everything arrives in the BGP L3 VPN.0 table. Okay. So, peering arrangement. We need to get some peering arrangement. We need to add some information to our BGP protocol. What do we need to add? We need to add this family INET VPN unicast information onto it. But now that we've added that, see, if we don't add anything, the default is family INET unicast. That is the default routing protocol that is used by BGP. As soon as we go and add another protocol, we then need to specifically add what was previously our default, which is our family INET unicast. So because we're specifically adding the INET VPN unicast protocol, we need to now specifically add the INET unicast as well. So we're going to add that into our BGP protocols. Once we take a look at what we're peering, our peering arrangements, we will see that we have added those two route formats to our peering arrangement. Show BGP neighbor. We're going to be seeing the fact that we have got this BGP L3 VPN table as well set up there, and we've also got a Pacific VPN table, so VPNA.net 0, which is our VRF table, will be there as well. Okay, so that was the preliminary stuff. PE router configuration. So all the VPN stuff, all the VPN configurations are on the PEs. The P routers are not involved at all. So we're going to create a routing instance and list the associated VRF interfaces. We're going to assign a route distinguisher that identifies that particular VRF table. We're going to link the table to import and export policies, or otherwise we're going to configure the VRF target statement right in the BGP protocol.
configuration within the table. In fact, in our lab, we're going to take the second approach. We are going to configure the PE-CE routing protocol properties. So how do the routes get from the CE to the PE and back? That may be BGP, it may be static routes, it may be whatever. We're going to set that up. Then we're going to set up the VPN policies. So we're going to create and apply the VPN extended communities. So the route table, the route target, or maybe the site of origin. We're going to set that up in policy. We're going to create the import and export policies if we are using import and export policies. Okay, so let's take a look at the characteristics of our network. So our provider core is a single area OSPF network. We are using RSVP signaling between our PE devices to establish our label switch paths. Little note here that CSPF is not required, although it is usually used. You don't need it, but it is the default, so it is normally used. So I expect that it would be part of the LSPs. We then check that we have got MP BGP peering between our PE routers, so we're peering between the loopback addresses, and we could set up, in this particular example, we're going to set up an eBGP peering arrangement between our CEs and our PEs. And we'll do that in our lab as well. We set up our lab. In our lab, we'll do both. We'll set up a static route between CE and PE, and then we'll get rid of those, and then we'll set up a BGP peering, just to kind of see what both of those look like. Okay, so we've got a full mesh layer 3 VPN between, so our goal is to have a full mesh layer 3 VPN between CEA and CEB. Okay, so we're going to create these VRF routing instances. We're going to create them under the edit routing instances hierarchy. We're going to give it a name. So here's an example, edit routing instance VPN-A. So simple as that. What is the instance type? It is a VRF. That is the instance type. That is a special type of instance that is specifically for these layer 3 VPNs. We will add an interface to our routing instance. We will add a route distinguisher to our routing instance. We will add a route target to our routing instance. Here's an example of a route distinguisher. So that's a type 1. We're going to add a route target. There's an example of a route target being added to our BGP configuration. Okay, we can use import and export policies. So there's two ways of going about it. There's specific configuration, or there's import and export policies. Both will work fine. And this is the, if we are using import and export policies, this is an example of what that policy would look like. So we've got our community VPN-A, and we're setting up the details of that community is a route target. We're adding that by policy. Okay. All right. So with these extended communities, where the target tags specifies the route target. So there it is. There we're specifying a route target, and we can have an origin tag as well, which specifies a site of origin community. It can be used to prevent running loops when a user has got multiple autonomous system numbers. So you don't have to use it, but it can solve certain problems. Alright, Juniper OS import and export policies can be applied to the routing instances, so we can then control what actually gets sent between the PE and the CE if we need to do that as well. So that's just an additional control over routing information. Okay. So here is a routing instance. We're applying an import policy on that particular instance. It's an example of that. Okay, now let's talk about some things that we may have to use in particular circumstances. The AS override feature. This feature is used when the CE routers belong to the same autonomous system. So here's the deal. You've got a customer, a large customer, which has got an autonomous system number given to them by IANA. And consequently, both sites, or all the sites in this case, that are involved in your VPN have got the same autonomous system number. The problem is that when you have got a BGP peering arrangement between your CE and your PE, the autonomous system will appear in the path statement of the BGP route, so that when the PE receives that particular route, it will advertise that BGP route to its PE peer. So the PE peer, which is attached to the other site, receives this BGP route with the autonomous system path statement in the route. Now the problem is the PE will not re-advertise that route to the CE if the CE is part of the same autonomous system, or if the autonomous system of that CE already exists in the path statement, because that would create a routing loop. So that is the default behavior. So to overcome that, and the thing is, we do want it to advertise those routes to that site, because those routes will not create a routing loop. They're actually, those routes have been originated from a completely separate site. So we're not creating a routing loop. So we actually do want to advertise those routes into that CE router. So to overcome the issue that the autonomous system of the CE is already in the path statement, you can use the AS override option. And we will use that in our labs. We'll actually see the effect of that in our labs. There's a couple of other ways of solving the problem. You can use the autonomous system loops option, or you can, if the CE are using a private autonomous system from the private autonomous system range, you can actually remove that from the path statement altogether to solve the problem. So there's not just one way of solving the problem, there's a few different ways of solving the problem. A few other things that we may have to do to solve certain problems is we can use this attribute here, this attribute set feature here. We use that when the CE routers belong to the same autonomous system and iBGP is used. So this is another way of sort of solving the same problem. It causes the PE router to use a new attribute called @set to carry custom attributes across a provider network, and the attributes are restored or preserved when advertised to the remote CE router. So this can be used to solve a specific problem. And the site of origin. Site of origin can be used when the CE router is dual home and AS override is required. So the site of origin prevents the advertising routes back into the source. So the site of origin is there to prevent routing loops, essentially. So normally the autonomous system number prevents routing loops by being included in the path, but if we are overriding that, then we need to use site of origin as well as a mechanism to prevent routing loops. If we're using OSPF between the PE and the CE, we need a separate OSPF process for each VRF table, and it's going to be carrying the OSPF routes across the background as BGP routes. And the two methods to advertise these routes between the customer sites, we would use an OSPF sham link, or we can use a domain ID. So these are OSPF mechanisms, part of the OSPF. Example of a sham link. So these are just sort of stuff that we may have to do in certain circumstances. Don't want to get bogged down in all this because it can get a little complicated. So just so you know, we can use this sham link if we do have to advertise OSPF routes across or between the CEs. A bit of information on that. We won't actually do this as a lab. OSPF configuration results there. We can also use this domain ID again. I don't want to really get into this for the purposes of what we are doing here today. I just want to focus on setting up a VPN. Okay. All right. So what we're going to do is we'll take a break. We'll go to lunch. When we come back for lunch, we're going to do two labs. We're going to do the setting up the baseline, the VPN baseline, and then we are going to go ahead and create a layer 3 VPN. First using static routes between our PEs and CEs, and then using BGP between our PEs and CEs. So let's go to lunch, and we will get stuck into this when we come back.